You're walking out of a subway station in an unfamiliar neighborhood. You have no idea which way is north, so you pull out your phone, open your map, and wait for that familiar little blue dot to show up and tell you exactly where to walk. A lot of people assume their phone is shooting a radio signal up into space, pinging a satellite to ask for directions. But if your phone actually had to transmit a signal thousands of miles through the atmosphere, your battery would drain to zero in a matter of seconds. Instead, your phone is completely passive. It is just listening. Up in space, about 12,000 miles above our heads, there is a network of satellites constantly broadcasting their own signals down to Earth. You can think of it like a giant cosmic game of Marco Polo. Right now, there are at least 24 active satellites shouting Marco over and over. Except in this game, Marco translates to, "Here is exactly who I am, where I am, and what time it is." That blue dot appearing on your screen is just the result of your phone doing some incredibly fast math, calculating exactly how long it took for those shouts from space to reach your hand. Those signals broadcast by the satellites are radio waves, which means they travel at a constant, reliable speed, the speed of light. Because the speed never changes, your phone can figure out exactly how far away a satellite is, simply by measuring the fraction of a second it took for the signal to arrive. Look at this model of the Earth. Imagine your phone calculates that it is exactly 12,000 miles away from a specific satellite. That means you could be anywhere on the surface of this massive bubble, which has a 12,000-mile radius centered on that satellite. Now, watch as your phone catches a signal from a second satellite and draws a second bubble. You have to be somewhere on the first bubble and somewhere on the second bubble. So your location is narrowed down to the exact circular ring where those two massive surfaces intersect. Add a third satellite to the map, and we draw a third bubble. The place where all three of these surfaces meet is no longer a ring, it is just two specific points. One of those points is usually floating way out in empty space, and the other is somewhere on the surface of the Earth. Finally, a signal from a fourth satellite draws one last bubble. That fourth bubble will only intersect with the true location on the ground, eliminating the false point in space. By finding the exact intersection point of four enormous distance bubbles, a tiny computer chip in your pocket can pinpoint your physical location anywhere on the planet. But this entire mathematical system rests on a knife's edge. Light travels extremely fast, about a foot every single nanosecond. If your phone's timing is off by just 1/1000th of a second, your calculated location on the map will be off by about 30 centimeters. The little quartz clock inside your smartphone is impressive, but it naturally drifts. If the system relied entirely on standard clocks, a tiny fraction of a second of drift would quickly multiply, placing your blue dot miles away from where you actually are. To keep the math perfectly aligned, we need atomic clocks. Instead of ticking using springs or quartz crystals, atomic clocks measure the unchangeable, incredibly rapid vibrations of individual atoms, like cesium-133. These atoms vibrate over 9 billion times a second, creating a perfect, unwavering heartbeat. For a large part of the 20th century, building machines capable of reading these subatomic vibrations was one of the greatest challenges in physics. Today, every single GPS satellite carries multiple atomic clocks on board. They are essentially the metronomes of the sky, ensuring that every Marco shouted down to Earth is stamped with a flawless, perfectly synchronized time. Without our ability to read the exact vibration of a single atom, those giant intersecting distance bubbles would instantly lose their shape, and the map in your hand would become a chaotic mess. Yet, even with perfect atomic clocks, engineers building this system ran into a massive, mind-bending wall, the laws of physics themselves, written by Albert Einstein. Because the satellites are moving in orbit at thousands of miles per hour, Einstein's theory of special relativity dictates that time actually moves slower for them compared to someone standing still on the ground. But this graphic shows a competing effect. According to general relativity, gravity also warps time. Because the satellites are thousands of miles away from Earth's heavy gravitational pull, their clocks naturally want to run faster than ours. As the calculation totals here, the gravity effect wins. A satellite clock will tick slightly faster, gaining 38.6 microseconds every day. It sounds tiny,
But in a system that relies on the speed of light, that drift would cause your map route to stray off course by over 7 miles every single day. To fix this, scientists have to rig the game.
Before launch, engineers intentionally tune its atomic clock to run slightly too slow. They build a purposeful error into the machine, knowing that once it reaches orbit, the warping of space and time will speed the clock up to the exact, perfect rhythm. If we didn't mathematically correct for the literal bending of time and gravity, our entire global navigation network would fail within minutes of being turned on. So the next time you step out of a subway station, pull out your phone, and wait for that screen to tell you where to walk for a slice of pizza, think about what is actually happening. In a fraction of a second, a small chip in your hand is catching invisible radio waves from space. It is measuring the speed of light to draw enormous, intersecting geometric bubbles across the globe. It is relying on the unwavering vibration of cesium atoms, and it is applying the math of relativity to correct for the warping of time and gravity above our planet. That little blue dot is a daily, perfectly executed triumph of human physics, mathematics, and engineering, resting quietly right in the palm of your hand.
Do you have any ideas for my next video? Just write them down in the comments below, and I will explain it in the next one. Don't forget to like and subscribe. Thank you so much for watching.